Now, this would be new stuff for many or most of you. We are talking about some of the measures of good software. When I'm talking about this, please see that this is different from things like program complexity that you have seen in ICS 240. Like, you know, that there's big O notation and stuff like that, that is related to the complexity of algorithms. That is not what we are talking about. We are talking about things such as modularity, cohesion, and coupling, which related to the way things are designed, not about their running times, but about how well they look for understandability, modifiability, testability, security, etc., etc. So what do we mean? When we build software, and we are now worried about building large software pieces, not a small program. So when we build a large piece of software, we want to construct it in such a way that they are in small modules, distinct components that interact with each other, but each component is independent in many respects. The independent modules are put together to build or to make the big system. So each module is an abstract data type that encapsulates some data and provides a bunch of operations. So dividing a large system into a number of modules helps us build the software in a more systematic fashion. There can be multiple people developing the different modules. They would be very independent of each other. And what we want for each module is that things within a module should be cohesive. They should be related to each other. For example, maybe as an extreme example, if you have a student class, which could be thought of as a module, you don't want to put things related to a faculty in that student class. They don't go together, right? Or things related to a course syllabus in a student class. They're two different things. There may be some interaction between a student and a faculty, but that doesn't mean that you should put faculty information into student. They should be separated. So within a student class, you only want to see things related to a student. So that is called cohesion. Are things related within a single class? The other thing is coupling. When you have a system divided into a number of modules, it is expected that these modules will be interacting with each other. That is a given. But then, how much is the code within a module dependent on code in another module? For example, a code in one module needs to know about the methods in some other module because it needs to call those methods. But how well can you arrange the dependencies so that even if one module changes, the other modules are not affected to any great extent? So the dependency between modules should be minimized. The dependency between modules or among modules is called coupling. You want to minimize coupling and increase cohesion. As an extreme example, if you have just one module for an entire piece of software, if the entire system is just in one module, then cohesion is very bad because you have everything inside one module. They are like, if you have a university, you have information about faculty, courses, students, staff, labs, library, everything in one place. So there is a lot of unrelated methods and data within the same module. So the cohesion is very bad, but there is no other module. So this module is not dependent on anything else. So trivially, coupling is zero, you could say. But this is a pretty bad system. On the other hand, if you start dividing up the system into modules, which you have to, you are going to start improving cohesion if you are careful, but then you start introducing coupling. So coupling keeps increasing if you increase the number of modules, but then you could design the modules in such a way that coupling is not a serious issue. Now, we all would like to have systems that can be modified later and can be tested quickly. That is, we would like to run our business with the least expense. If you have to modify a system because changes are coming or because you noticed a bug, you would like to do that quickly so that you don't have to spend a lot of money on it. And you can get your system corrected quickly or changed quickly, right? So modifiability is important. When you are modifying a system or when you are creating the system from scratch, you need to test your system. So whether you can test your system well is another aspect. So there are two good or desirable features. One is modifiability, the ability to change a system, and the other is testability, whether a system can be tested easily. If you have low cohesion, then it is more difficult to test it, more difficult to modify it, because you see unrelated data, unrelated methods. So testing those things would be more complicated. Modifying things, you could introduce more errors. And if you have high degree of coupling, again, you can't test something independent of others. So it becomes more difficult to test. If you have a high degree of coupling, then modifying one would affect another. So it would be more difficult to modify. The other aspect we will spend some time in this course is secure coding. What do we mean? Well, security is a big issue in computing. People try to profit from vulnerabilities in software by hacking through viruses. Then they demand money. I mean, they corrupt a system, they get hold of a system and then demand money, ransom. And then only if you pay money, then you will allow the owner of the computer system to get the data back, and so on and so forth. You have heard about all those kinds of things. So can you design and implement a system so that these vulnerabilities are reduced? So secure coding is the employment of proper coding practices to minimize or even hopefully eliminate software vulnerabilities. So these are measures of good software. Then some more things that you may not have seen much in previous classes. What are the advantages of object-oriented systems? Objects represent real world entities. So it is a little more natural to use this paradigm. It improves productivity because it allows more reuse of software, more parallel development, promotes more cohesion and less coupling. If you employ the proper design and implementation practices, you can modify things more easily and it reduces risk. So there are a lot of advantages. So this is the preferred way of designing and implementing software systems these days, the object-oriented paradigm. So it is important for you to understand this paradigm well. Object-oriented systems have more layers of software, so they tend to be less efficient in terms of execution time. And for many people, the paradigm is a little hard to learn, but once you learn it, it is pretty easy to use. Then a little bit about the history of the paradigm. Maybe the earliest days of the paradigm could be around late 60s with a similar programming language, where there was the idea of a class. Then Smalltalk came, I think, towards the end of 70s or by 1980 or so. Then C++ was a language developed out of C and Simula. It started as a PhD project at the, I think in Cambridge by Strostrup, who came over to the US and worked at Bell Labs. Then he came up with C++. Then it was introduced, the idea of objects was introduced in Lisp, and Java came in 97, was released in 97, I think, based on C++, but as a cleaner language, avoiding some of the more difficult concepts in C++. Design patterns, the idea of design patterns, we talked about this, right? The solutions, the common solutions to common problems, right? That is essentially design patterns. There was a landmark publication in 1996 or 98, I don't quite remember, by a gang of four, so-called gang of four. It's a fantastic book. I think you will benefit reading it at some point in time, maybe not right now, but maybe sometime in the middle of this course or after you complete this course, you would have enough background to understand that book. Otherwise, it is going to be a very difficult to read experience. It will be pretty dry and you will not appreciate it. And you may be put off. So don't look at it now. Wait a few weeks at least. Then unified modeling language, again, I think came probably late 90s, early 2000s, from a consortium of research organizations, businesses. This has the name unified, meaning there were a number of different approaches for documenting object-oriented systems. So this was a kind of a unified approach, took ideas from a large number of sources and put together this documentation system called UML. It is nothing but documentation. Now, in succeeding videos, we will look at concepts that you have seen before, like classes, objects, fields, methods, etc., etc. And we might look at slides for some of these concepts, or we might just look at some examples in other cases, or use the whiteboard for explaining things. So the approach would be dependent on the topic, but the concepts will be covered very quickly, because these are things that were covered in ICS 141 and 240. So I don't have any intention of covering them in detail, because that would take many weeks. So we can't afford that.